Okay, so it's great to introduce Michael Hutchings from Berkeley. And Michael, he'll tell us about dynamical zeta functions of open symplectic domains.
All right, thank you very much for the invitation. I'm always happy to come here, and thanks to the organizers for organizing this wonderful conference. Now, I understand some people might still be recovering from the conference dinner, so I'll try to provide some light entertainment here. Okay. So the general question would be to try to classify open domains in R2n up to symplectic dimorphism and the connection with dynamics is, in particular, in the case where the boundary is say, star-shaped, you could say, to what extent does the domain see the dynamics on its boundary? And here's a more specific question which got me thinking about this. So is every convex domain symplectic dimorphic? Convex open domain, of course. All my domains are open today. So every convex open domain symplectic dimorphic to a toric domain. So remember, toric domain is where I start with some domain in Rn, and the toric domain is x omega is the set of z and Cn such that pi times absolute value Z1 squared through absolute value Cn squared is an omega. So these are nice examples where you can do lots of computations. In particular, the strong Viterbo conjecture is true for toric domains in 4 dimensions. So this is, if the answer to this question were yes, then that would imply the strong Viterbo conjecture in 4 dimensions. And this question seems kind of optimistic, and I was like, that can't be right. So, but how do I disprove this? So the answer is basically no. There's a little asterisk, which is that, well, as you'll see later, I can give you examples which are not symplectic dimorphic to toric domains, but there's a genericity issue. So I can prove that it's, for sure, it's not symplectic dimorphic to a generic toric domain. For completely arbitrary toric domain, there's a bit more technical stuff, which I think I can handle, but I have to get it all written down to be sure. And let me tell you about some tools that you can use to address this kind of question. So take your favorite version of contact homology. And to avoid some algebraic annoyance, with coefficients in a field. And the examples that I'll be talking about today will be either ECH for the contact 3 manifolds, well, in general, it has Z coefficients, but you can use Z mod 2 coefficients. Or in general dimensions, at least for star-shaped hypersurfaces in R2n, we can use the S1 equivariant symplectic homology. Which again, you could use Z2 or Q coefficients. You can identify this with linearized contact homology, or you can think of it as linearized contact homology, except as far as I know, a completely rigorous foundation for linearized contact homology is still lacking, but this S1 equivariant symplectic homology is sort of, to the extent that this is defined, it's the same as this. So you can use the SHS1 as a substitute for it. Okay, so you pick a favorite contact homology. Now, if I have X a domain in R2n, with smooth boundary, so the boundary is smooth, star-shaped, and non-degenerate rate flow, then you can apply whatever kind of contact homology you like. And this will give you a barcode. I actually want to use a Z2 graded barcode. And so this is very standard stuff for people who work on this sort of thing. For those of you who don't work on this sort of thing, and I'm kind of a beginner at it myself, the basic idea is simple. The idea is you have whichever version of contact homology you're talking about, you've got a chain complex generated by Rabe orbits or some sets of Rabe orbits or something like that. And each generator has a symplectic action, and the differential decreases the symplectic action. And by some linear algebra, you can decompose the chain complex into a direct sum of two-term chain complexes. And for each of these two-term chain complexes, you draw a bar, and these bars are going along the real line. So a bar like this indicates that, you have an element of the chain complex here. So this is like a new basis for the chain complex. So the endpoints of this bar are two basis elements for the chain complex. And the R values here are their filtration levels, and then there's a differential. And when the homology is non-trivial, there's some infinite bars. So there's some generators that never get killed. And then the R value associated with such a generator is its filtration level. Okay. So you can decompose the chain complex into a bunch of bars like this, and they have signs because there's a Z2 grading on the chain complex. So each endpoint of a bar is labeled by plus or minus, depending on whether its grading is odd or even. And if you have a bar, a finite bar, then its ends have opposite sign, because the differential decreases the gradient by 1. And you can draw some more bars, whatever. You can have multiple bars which are the same. That's all right. Okay. And then there's an algebraic lemma, which is that this barcode is well defined. So there might be different ways to decompose a chain complex as a sum of two-term chain complexes, but you always get the same barcode as a result. Okay. So this barcode is an invariant of this of the boundary of X. And then there's a standard metric on this space of barcodes. So there's a bottleneck distance on the set of barcodes. By the way, there's one little minor thing. When I take these R values, for reasons which will become clear in a minute, I actually want to take the log of the symplectic action. And I want to do that so that if I scale the whole domain, then it just shifts all the bars over by a constant amount. Okay, so the bottleneck distance is the distance from barcode 1 to barcode 2 is the infimum over epsilon such that B1 can be transformed into B2 by moving endpoints of bars by distance less than or equal to epsilon. And you can also add or delete bars of length less than or equal to 2 epsilon. Okay. And then if I take a, now let's take a more general domain, an open domain, which can be C0 approximated by smooth star-shaped domains. And what I mean by that, I won't write the whole thing down, I'll just draw you a picture. So if here's X, and maybe it's got some kind of rough boundary, I don't know. So I can find some nice domain with smooth boundary, which is inside of X, and then a scaling of this nice domain by some small amount, which is outside of X. So I can sandwich the boundary of X in between two smooth star-shaped hypersurfaces, which are arbitrarily close together. So that's what I mean by it can be C0 approximated by smooth star-shaped domains. And then if I have such a domain, well, I can take these approximating nice domains, and each of them has a barcode, and I can take a sequence of these domains which is converging to X, and you can show that you actually get a Cauchy sequence in the space of barcodes with that metric. So this leads to a completed barcode in the completion of this space of barcodes. And this is a symplectic invariant of X. So to repeat, I take any open domain which can be approximated by smooth star-shaped domains. Pick your favorite version of contact homology. Then you get a completed barcode, and it's an invariant of the domain. And so now what can you do with this? Well, you can do a lot with this. So let me now tell you about something you can do, which actually, it throws away a lot of information, but it still is enough to tell you some useful things. So if the completed barcode is actually a barcode, so the set of barcodes injects into its completion, then you can define the zeta function so zeta, and you have to put a subscript to say which kind of contact homology you're talking about. So it could be ECH, or it could be SHS1 plus, or something else of X. And this is the sum of the endpoints of bars of plus or minus 1, depending on the grading. So remember, each endpoint of a bar has either a plus sign or a minus sign. And then times t to the action. So each endpoint of a bar also has an action associated to it. And this is some formal power series. It's an element of the universal Novikov ring. Yes? Does it depend on the choice of what? No. So if you have two approximations, they're converging to the same point in the completion. Yeah, it's because of the C0 continuity of contact homology. Yeah?
For target domains, are there finite bars? You say if you use this one equivariant.
Yes, there are finite bars.
There are finite bars?
Yeah. Lots of them, in fact. Yeah?
Sorry, could you say one more time how you determine the grading of the...
So that depends on which kind of contact homology you're talking about. So I guess I should have said, I guess I erased it already, but when I said choose your favorite version of contact homology, that part of its structure should be a Z2 grading. So like for symplectic homology, the grading is the Conley-Sanger index, usually shifted by n-1. For ECH, there's the ECH index, et cetera. Yeah?
If you go with the barcode from low action to high action, the first bar is always going to be infinite, or can it be finite?
In general, the first bar could be finite. Yeah. Yeah. So I think not. Like, if you do this construction, you'll always get a countable number of bars. This is non-obvious, but. Okay, so that's the zeta function. So the zeta function really throws away a ton of information. Like it tells you what these points are, but it doesn't tell you which point is connected to which by a bar.
The function, just the function is Euclidean degenerate function with
Uh,
point something like a Cantor set, or a Cantor set of critical value.
Well, you can certainly get a whole lot of bars in this completed barcode.
But it can't be two number.
I think so, yeah. We can discuss more afterwards. Anyway, what the question you're asking is related to why I put an asterisk in the answer to my question. So for really bad stuff like that, the zeta function certainly won't be defined, and I have to say things differently to prove something. Okay, so why do I like this zeta function? So here's the ECH zeta function has a really slick form. So if x is at R4 and boundary of x is non-degenerate, so zeta ECH of x is the sum over alpha an ECH generator on the boundary of x. And Brian yesterday reviewed what these are. In case you forgot, I'll tell you in a second. And we have -1 to the ECH grading of alpha times t to the action of alpha. And what's an ECH generator? So it's a finite set of pairs. Alpha equals alpha mi, alpha I comma mi, where the alpha I are distinct simple rate orbits. If alpha I is hyperbolic, then mi equals 1. And the action of this orbit set is just the sum over I of mi times the action of alpha I. And there's another fact, which is that the -1 to the grading, I won't tell you the whole formula, but I can tell you the pairing of the grading is very simple. This is -1 to the number of positive hyperbolic orbits. So in this three-dimensional case, non-degenerate, every orbit is either elliptic, so the linearized two-term map is a rotation, or it's hyperbolic, which means that it has real eigenvalues, and they're either both positive or both negative. Is there a question? Okay. So that's what the generators are. And then if you think about that for a minute, that lets you write this zeta function in a slick form. So you get that zeta ECH is the product over gamma a simple Rabe orbit, with action A, and then there are three cases for what the factor is. So it's 1 minus t to the a inverse if gamma is elliptic. It's 1 minus t to the a if gamma is positive hyperbolic. And it's 1 plus t to the a if gamma is negative hyperbolic. So you just think of this as a generating function. If you multiply all this stuff out, then the coefficient of t to a given power is a number of ways of for each of these factors. So if you remember this thing, this expands as 1 plus t to the a plus t to the 2a, and so on. So this says that for an elliptic orbit, you can take it with any multiplicity. For hyperbolic orbits, you can only take them with multiplicity 1. The negative hyperbolic orbit is even grading, and the positive hyperbolic orbit is odd grading. Okay. So that's the ECH zeta function. And there's an even more slick way you can write this, which actually makes sense in any dimension. So you can write this as the exponential of the sum of gamma a Rabe orbit, not necessarily simple, of minus 1 to the epsilon of gamma. So what epsilon of gamma is you look at you think of gamma as a fixed point of a return map, and this is the sign of that fixed point that appears in the Lefschetz fixed point theorem. And you divide by d of gamma. So if gamma is a simple orbit, then d of gamma is 1. If it's a multiple cover, then d of gamma is the covering multiplicity. And then you multiply by t to the action of gamma. So it's a combinatorial exercise to check that these two formulas are the same. But this last formula, this makes sense in any dimension. And I should call it something else because ECH doesn't exist in higher dimensions. So let me call this zeta Lefschetz, because there are zeta functions kind of like this. There's a long history of them. And Lefschetz is the one person I'm sure is not responsible for it. but it has like signs from the Lefschetz fixed point theorem in it. So I looked at something similar to this in my PhD thesis back when the world was still black and white and populated by dinosaurs. This goes back to a paper by Andre Weil in the 1940s in number theory. Okay, so that's this function. So here's a proposition. In any dimension, for a non-degenerate, well, for an open domain, whose boundary is star-shaped, smooth, and non-degenerate, and this zeta Lefschetz is a symplectic invariant. So let's call this X. the symplectic invariant of X. And yeah, so I talked about this at Aubry in June, and I remarked I didn't know if that was true or not, and I figured it out like hours after giving my talk, so it's true. And the, sorry?
What coefficient does it matter what coefficients?
Coefficients. What coefficients I take where?
So the Lefschetz formula, this Lefschetz zeta function is independent of the coefficient.
Yeah, this is just a generating function. It's in a Novikov ring with Z coefficients. So in the proof is, so I didn't tell you, you can also make a zeta function for S1 equivariant symplectic homology, which you can regard as generated by good Rabe orbits. So you take this thing, maybe I'll call it LCH just to emphasize that it's generated by good Rabe orbits. And out of this, you can by an algebraic operation, you can make this Lefschetz zeta function. And what this operation is, it's a multiplicative homomorphism sending, if you take t to the a, then this goes to the product over all non-negative integers of 1 minus t to the ka times mu of k, where this is the Möbius function, which is 0 if k is divisible by a square, and otherwise it's 1 if k has an even number of prime factors and minus 1 if k is an odd number of prime factors. So that's just a cute little fact. Now, okay, we still have some time. So let me get back to the question I was telling you, I asked at the beginning, is every convex domain symplectomorphic to a toric one? So proposition for a generic toric domain in R4 where I guess I should say star-shaped. Where the set omega is its boundary curve has endpoints at the points a comma 0 and 0 comma b in the plane. So if I take the inverse image of this set under the moment map to get a toric domain in R4, its zeta function is 1 over 1 minus t to the a times 1 minus t to the b. That's it. So it's a very simple formula for the zeta function. And what does generic mean? Well, I'd like this curve to only have finitely many inflection points. That would be good enough. So this, what's the idea here? So there are two elliptic orbits corresponding to these endpoints of this curve. So the endpoint, the inverse image of this point under the moment map is an elliptic orbit with action A, and the inverse image of this point is an elliptic orbit with action B. So by that product formula for the zeta function over there, those two elliptic orbits contribute this denominator here. And then I'm saying there's nothing else in the zeta function. So there are a lot of Rabe orbits and bars, but they all cancel out if you're counting them to make the zeta function. So what are the other orbits? For every point on, let me give this curve a name. So this curve, which is the, I'll call this boundary plus of omega. It's the boundary of omega, not including the axes. So for every point on boundary plus omega with rational slope, there's an S1 family of Rabe orbits. Now you can perturb the contact form in a neighborhood of such an S1 family to make one elliptic orbit and one positive hyperbolic orbit, whose actions will be very close to each other. So they'll cancel out in this zeta function. In the limiting bar code, you're going to have two endpoints of bars with exactly the same action, but with opposite signs. So they cancel in the zeta function. Now, this is this zeta function is very special looking. Like, if I took just a random domain in R4, I'd expect I wouldn't. Well, generically, you expect infinitely many. Well, generically, actually, no. There are infinitely many Rabe orbits, and you expect they're not going to all cancel out in the zeta function like that. So you would expect that for a random domain in R4, it's not going to have a zeta function looking like that. So it's not hard to make examples. So I'll show you another example. This is much more difficult than needed to make something a zeta function doesn't look like that, but it's a nice example. So for a generic Morse function, f from S2 to R, you can look at a contact form on S3. So S3 fibers over S2 with fiber S1 by the hop vibration. I could denote this map by pi. So you can take the standard contact form and multiply it by e to the pi star f. And this corresponds to a star-shaped domain where I forgot, we start with the sphere and then of radius 1, and then you each point you move it out by, I think I want to put I forgot if I want like f squared or log f or something. Anyway, you stretch this out by some amount determined by f. So you get an appropriate star-shaped domain. Let's close down to f. So that's really just the setup for my proposition. So what does my proposition say? Sorry, my board work here is a little disorganized. But let me put the proposition inside these boundaries here. So the conclusion of the proposition is that the zeta function of this toric domain is the product over P, a critical point of F, of 1 minus T to the action, which is going to be e to the P, e to the F of P. And then this is going to be an elliptic orbit if the critical point has even Morse index and a positive hyperbolic critical point otherwise. So I raise this to the power minus the Morse index of P. So it's a product of terms of the form 1 minus T to the something to the plus or minus 1. One of these for each critical point of F. And the idea is, again, so these critical points give you Rabe orbits, which are either elliptic or hyperbolic orbits, and the other critical points, it looks kind of similar to the toric picture. So the other Rabe orbits come in S1 families, which cancel out after perturbation. So you can, like if I have a Morse function with, say, one saddle point and 2 minima and 1 maximum, you can easily see it's not gonna look like this. So such a domain can't be symplectomorphic to a generic toric domain. And also, you can take this function f pretty close to 0, and so this domain xf is going to be close to the round sphere. So the conclusion is that there exist open domains with smooth star-shaped boundary which are arbitrarily close to S3. So the domain is X, boundaries Y. Such that X is not symplectomorphic to a generic open toric domain. And I think I can get rid of the generic here, but I'm still working on that. Are there any questions about that? So for the toric domain, so it would be sufficient. It's sufficient to assume that this curve here has only finitely many inflection points, And then for any given rational slope, I'm only going to get finitely many S1 families of Ray orbits. So that's enough to keep the barcodes under control. So I'll only have, up to any given action, I'll only have finitely many bars. And then I have a well-defined zeta function. The actual bar, if you look at the actual barcode, it can be much more complicated. Other questions? Okay, so if you look at the barcode, it contains more information. So I'll tell you a bonus theorem. So let X be a convex or a concave toric domain in R4. So a convex toric domain is one where the set omega is itself a convex set, and I want the slope here to not change sign. So the general definition in any dimension of convex toric domain is you take the set omega, and then you take all of its reflections across all the axes, and you want that whole set to be convex. That's a convex toric domain. And a concave toric domain is one where omega looks like this. So I want the first quadrant minus omega to be a convex set. This is a concave toric domain. The terminology is a bit bad, and I'm partly responsible for this. So a convex toric domain is not exactly the same thing as a toric domain which is convex. I'm sorry. So it is true that any convex toric domain is convex, but there are also some concave toric domains which are convex. If this curve isn't sort of not too concave, then the toric domain will still be convex. Sorry. Anyhow, so I need to give you a conclusion of the theorem. So the conclusion of the theorem is, and this is an open domain, then the X up to symplectomorphism determines omega up to reflection across the diagonal. So for any toric domain, I could take the reflection of omega across this diagonal. That corresponds to the symplectomorphism of Z2 switching Z1 and Z2. So certainly no symplectic invariant is going to notice that. But modulo of that, the toric domain, the symplectomorphism type of the toric domain determines the toric domain. So if I have two convex toric domains, if their interiors are symplectomorphic, then their boundary curves are the same up to reflection. And a remark. So for if the boundary curve is real analytic, this was proved by Moati. In 1994. So it's actually, the proof is kind of, what he proved, a sort of, a different way to say what he did is he proved that the symplectomorphism type of the toric domain determines the germ of this boundary curve where it intersects the diagonal. And if it's real analytic, then the germ of the curve at this one point determines the whole thing. So this, and then this thesis is similar to stuff which Jean-Good and I, some calculations which Jean-Good and I did many years later. So this was way ahead of its time. I guess nothing we do is really original. Anyhow. Sorry? The action spectrum. No, the action spectrum's not good enough. So, so I'll tell you the idea of what's going on here. So the idea of the proof so you need to, I guess while we're talking about precedents from a long time ago, I should have said before that, so also in the 90s, Seeley, Black, Fleur, and Hofer showed that for non-degenerate domains, or for domains with non-degenerate boundary, the symplectomorphism type of the domain sees the Rabe orbits on the boundary and their Conley-Zander indices. Which is almost enough to determine the zeta function. Okay, now the idea of the proof of this theorem, so as we said before, well, there's a S1 family of Rabe orbits. For each point on the boundary curve. Where it has rational slope. And if I have such a point, so here this slope is some rational number, I can look at the tangent line to the curve at that point. That's not a very good picture. Imagine this line is tangent to this curve at this point. Okay, so the slope is rational, and then the symplectic action actually determines where this line is. So if you know the slope and you know the action, then it tells you exactly where that point is. It's determined by the tangent line. So if you just look at the action spectrum, so you look at the actions of all the Rabe orbits, that's going to tell you the actions of these various generators, but it's not going to tell you which action corresponds to which slope. Okay, so for a convex domain here, well, it's the intersection of all the half spaces containing it. So if I know for every rational slope, what is the tangent line with that slope, then that determines the domain. And the symplectic, so if I know which symplectic action corresponds to which slope, then I'm good. A priori I don't, but the completed barcode gives me the necessary information. It's more subtle than it looks at first glance, but in any case, the completed barcode determines which symplectic action corresponds to which slope. And the barcode for SH is 1 plus. So by carefully studying this completed barcode, you can, which actually is just a barcode in this case. You don't need, it's an honest barcode. So by carefully studying that barcode, you can determine all of the tangent lines to this domain with rational slope, and that determines the domain. So that's the idea of that. So that's a little fun. Yeah, I guess that's it for me. So thank you.